Hello everyone, welcome to this fourth session on switching theory and logic design. Myself Dr. Sohail Rana, and we are going to study the number systems in this session. We will continue our previous session discussion where we were discussing the examples on the conversion. So let us move ahead with our today's session. So last time we were discussing about the double method. So we have seen one example last class where only integers were involved. Now this time we will see one example where fraction is also involved, so that these type of examples will be perfect. So let us see one example. The example question is to convert 0.75 to binary. This is decimal number using the double method. So we have to use double method. So now what is the procedure? We have to multiply the given fraction by 2 and we have to keep the integer in product as it is and multiply the new fraction in the product by 2, and we have to continue this process, and we have to count it from top to bottom. In integer we considered from bottom to top. For fraction we will consider from top to bottom. So now let us see. So given fraction, what we have, say we'll make one table, so you will get it clear idea about it. Say we'll insert one table, say 2 by 2. Okay, so we'll use this one. Okay, on this we will check. So here we will take one. Say we have to write down the given fraction. So given fraction we will write down given fraction. Given fraction is say 0.75. It is disappearing here again. I hope it will appear. Anyway, we will not use this table. We will do this without table. So here say okay. So first we'll write down, say given fraction. Given fraction is 0.75. Then what we have to do? We have to multiply. This fraction by 2. So what we will get? 1.50. Then next what we have to do? The answer we will multiply by 2. So what we will do now? We have to repeat this process. So we will multiply 1.50 by 2. So we'll get we will multiply 0.5 after fraction number 0.50 by 2. So we'll get 1. So now there is no fraction here. So what is our answer? We will consider from say top to bottom. So top to bottom we will write down say 0.75 decimal equal to 0.11. So here we have dot after 2. So after leaving 2 we will give one dot here. So this is the answer for this example. Now let us consider another example where we will keep both fraction and decimal. So let us take this example. We have example of the number given is say 105.15 base 10. We have to convert it to binary, right? So we will use same successive division we will use, and we will see the conversion. So first we will focus on 105. Say first of all we will simply do for this one we have to do successive division, and for this we will do successive multiplication. So first one by one we will solve. So let us take 105 only. So first we will use this and we will see. So we have to do successive division by 2. So we will divide it by 2. Say we will get then 105 by 2. So this 2 we divide, then we get here 52. Remainder will be 0 here. Then again we will divide by 2. So what we will get 26 here. So here we have 1, 0. Then we will have again divide by 2. We have 13. Then again divide by 2. We have 6, remainder 1. Then again we divide by 2. We have 3, remainder 1. Again 2. Divide by 3, we have 1, then again 1, then finally 0. So here we get 1, 0, 0, 1, 0, 1, 1. Now these numbers we will arrange from bottom up sequence. So here 105 base 10 will be equal to 1, 1, 0, 1, 0, 0, 1. This is binary. Now second we have to solve this. For that we will use successive multiplication. So successive multiplication we will perform on the fraction number, that is 0.15 base 10. So what we will do in this, we have to convert it. So first step, multiply by 2. So what we will get? So here first it was 0.15, then 0.30, then second multiply this again by 2. So 0.30 we will get 0.60. Third again we have to multiply it. So we will get 1.20. Then fourth again we have to multiply it. We will get, say, after decimal we will get 0.40 if we multiply with 0.20 only. And then fifth step again we will multiply it, we will get 0.80. Then sixth again we will multiply, we will get, say, 1.60. This particular fraction can never be expressed exactly in binary. This process may be terminated after few steps. Now reading the integer from top to bottom, we have to, after one limit we will stop it, top to bottom we will note down, say 0.15 base 10 will be equal to 0 point after this, then 0, 0, 1, 0, 0, 1 base 2. And the final result for 105.15 decimal will be equal to 110 1.001 base 2. So this will be the final answer. Now this is example. Now let us see another binary addition. So let us now discuss about the binary subtraction. So let us check out example. Say here we have the example. We'll write down example there. Now before writing example, we should also see the rules. Fine, first we'll write down the example. Example is say 111.1112, and we have to subtract it from 101.01. Right. Before that, we will see the rules. We have to remember the rules for the subtraction also. Those are very simple and interesting rules. 0 minus 0, of course, that is 0. 1 minus 1 is also 0. 1 minus 0 is 1. But when we do 0 minus 1, it will be equal to 1 with 1 borrow. Right. Now, by using these rules, we can solve the example. So let us solve it. Say we have 1010.010, then we have 111.111. Simultaneously, all of you should solve this example. 0 minus 1, we get 1 with borrow 1. So 1 minus 1, 0, then 1 minus 0, 1. It's no borrow. Then 0 minus 1, we get 1 with 1 borrow. 0 minus 1, we get 1. And 1 minus 1, we get 0, already 1 borrow is there. 1 minus 1, 0, 0 minus 1, 1. Again we have 1 borrow. 0 minus 1, 1, 1 minus 1, 0. Again we have 1 borrow. That 1 borrow will minus with this 1, so we'll get 0. So our final answer is 0.111. Right. So in this way we can solve the subtraction of the binary. Right. Now as we have this subtraction, similarly we can have the multiplication. So let us see examples on binary. So multiplication. So as we have rules for addition and subtraction, similarly we have rules for the multiplication. So multiplication rules are similar as we have in our normal multiplication. So like if we do 0 multiplied by 0 will be equal to 0. Then 1 multiplied by 1 will be equal to 1. Say 1 multiplied by 0 will be equal to 0, or 0 multiplied by 1 will be also equal to 0. Now the paper method is similar to the multiplication of decimal number. We have to multiply the multiplicand with each bit of the multiplier as we do in the normal multiplication. We get some partial product. Partial product is the same as the multiplicand if the multiplier bit is 1, and partial product is 0 if the multiplier is 0, because if we multiply anything with 0 we get 0. So let us see one example. Say example on multiplication. So we have question like multiply 1101 binary by 110 binary. So normal multiplication, how we write, we will write it down 1101 multiplied by 110. First we will multiply with this 0, these 4 digits. 0 multiplied by any number is 0. So here we get 4 zeros. Then below this we will write plus. Then we will multiply with this 1 with all these 4s. So we will get 1011. Now we have 2 plus. So we will multiply this 1 with this 4. We will get 1011. So let us check the answer. 0 will be as it is here. 0 plus 1, 1. 0 plus 0, 0. 0 plus 1, 1. Then 0 plus 1, 1. Now 1 plus 1 will be 0 with borrow 1. 1 plus 1, 0 with borrow 1. This borrow will shift here, and this will be our answer for this multiplication. So let us see one more example on multiplication. So the example is multiply 1011.102 by 101.01. So like same steps we will take here. So let us write down. We have 1011.102 multiplied by 101.01. So let us do first with the 1. So if we multiply with 1, we will get entire number as it is. Say we will get 1011, and sorry, this is also 101. We don't get 2 here actually. There is no 2 in binary number. We have to remember it. So then after this we will get this same number 101. Then next we have to multiply with 0. So we will get all zeros. Here we will write 1, 1. So how many are there? 1, 2, 3, 4, 5, 6, 7. 7 zeros. So here we go 1, 2, 3, 4, 5, 6, 7. Now the third one. Now third one is 1. So by 1 we will get the same number. So from here we will start, say 1, 0, 1, 1, 1, 0, 1. Now next step, again we will add one more plus here. Now with this 0 we will multiply, so all will be 0. So we have 7 zeros, 1, 2, 3, 4, 5, 6, 7. 7 zeros. And again at last we have 1. So we will multiply with this 1. So we will get this same number. So here we have 1, 0, 1, and 1, 1, 0, 1. And these are our partial products. Now we have to do the addition. So this one will come here as it is 1. Then 0 plus 0, 0. Then 1 plus 1 will get 1 plus 1 we get 0 with 1 borrow. Then 1 plus 1 we get 0 with 1 borrow. 1 plus 1 0 borrow 1. Then again 1 plus 1, 0, borrow 1. Then it will shift. We have to put decimal here. It will shift to next. Then 1 1 0 plus 1, we get here 1. Then 1 1 0 0 1, say 0. Then here we will get 1. Then again 1 1 and 1. So this will be the multiplication answer. Now as we have multiplication, similar way we can have the division. So let us see example of division. So here we will see, say, binary division. Let us now see the division. Now division, say we will solve division by the same method what we do in routine. So say binary division we will do. So in binary division, say we will take one example. Say we take the example as divide 1 0 1 1 0 1 binary by 1 1 0. So this is our example where we want to perform the division. So normal method how we use for division we can apply. So say we'll have 1 1 0 and we want to divide 1 0 1 1 0 1, right? So first we will divide with 1 1 0. So here we can have direct 1 1 0. We can write here say 1 1 0. So if we subtract this, we get 1 0 1 0. Again we can divide by 1 1 0. Here we will get 1, then second 1. Then we will subtract it. So we will get 1 0 0 1. Again we can subtract it by 1 1 0. Here we will get one more 1. So this subtraction we will get 1 1 0. And this 1 1 0 again directly we can divide by 1 1 0. Here we take some decimal and finally we get here 0. So this is the answer for this division. Now let us see one more example of division. So here example 2 we will write down. Say divide 1 1 0 1 1 1 0 1 0 1 0.11 base 2. We are divided by 1 0 1 base 2. So let us divide it. Now we have, we'll write down, say 1 0 1. We have to divide 1 1 0 1 point, sorry, 1 1 0 1 0 1.11. So directly we'll write 1 1 here. After that we'll give point. So first we can divide by 1 0 1 itself, 1 0 1. So here we'll get 0 minus 1 1, borrow 1 1 minus 1. Say there we'll get 1 1 0. This shift will shift this 0 here. Here we'll get 1. Now again we can divide it by 1 not 1. Then we'll get here 1 1 1. Here we'll get 1. Then again we can divide it by 1 not 1. So we get 1 0. We'll take 1 down. This 1. Here we get sorry, this one will be 0. Then we'll get 1. Then again we can multiply it by 1 not 1. Here we take 0, then decimal. Here we get this additional 1. Here we get 0, and here we get 1. So this is the division of two binary numbers. Now let us see representation of signed numbers and unsigned numbers. So what are the signed numbers, how to represent them, and what are the unsigned number, how to represent them, we have to see that. So say our topic heading we'll write down here. Our topic is say representation of representing signed numbers, right? So we have seen 1's complement and 2's complement, and there will be a method of writing number. For example, suppose if we have in sign magnitude form we want to write. So when we represent the binary numbers, so there will be one sign bit. The sign bit will represent the sign, either it is positive sign or negative sign, and remaining number will be the magnitude. For example, if I want to represent plus 44 number and I want to represent minus 44 number, then how can I represent this plus and this minus? First, let us write how we write the say plus 41. So there will be magnitude of 41, we will write as say 1 0 1 0 0 1, for example, right? So this is say magnitude. Now if it is plus, then here we will write plus 0. So this one will be called as sign bit. What we will call it? We will call it as sign bit, and this is our magnitude. So this number will be considered as plus 41. Now minus 41, how to write? The magnitude will be same. Say we'll have 1 0 1 0 0 1. The magnitude of 41 is same. Here for sign, there 0 means positive. So what will be the negative number? Negative number will be 0. So in place of positive number, we have to write the 0. So in that way we can represent the sign numbers. Now let us see one example for this. Say we will take one example, and we will also see the 1's complement and 2's complement by solving this example. So what is 1's complement? 1's complement means just we will reverse, we will invert the input. So 1's complement means if 0 is there, we will make it as 1, and if 1 is there, we will make it as, if 0 is there, we will make 1, if 1 is there, we will make it 0. This is nothing but 1's complement. So for example, 1's complement of 1 1 0 1 1 0. So its 1 complement will be opposite of these numbers. So this will become 0, this will become 0, this will become 1 0 0 0. Right? So this is 1's complement. And what is 2's complement? If we add, so this is 1's complement. If we add plus 1 in the same 1's complement, the answer will be 2's complement. So this will be 1 1 1 1 1 1. That is our 2's complement. This is how we find out 2's complement. Now we'll combine this example with the sign bit. So let us take one example for this. So let us have our example on this. Express -45 in 8-bit 2's complement. Right, so let us answer it. Now first thing, in 8-bit form, -45 plus, sorry, it's a shift example, this is given, okay, minus given. How plus 45 is written, first I will show you. Plus 45 is given 0 0 1 0 1 1 0 1. So this is for 45. Now we can use two methods. First method, what we will do, we will find out the ones complement of this number and add 1. So say we will write here the number 0 0 1 0 1 1 0 1. Its ones complement will be 1 1 0 1 0 0 1 0, and its 2's complement, what we have to do, we have to plus 1. So their answer will be 0 plus 1 1. Rest of the number stays as it is. Right, now this is the 2's complement of -45. -45 is already sign bit is 1. Okay, now this is the method by using which we can find out the 2's complement. Now let us see one more example. Say next example we will see. Say next example is express -73.75 in 12-bit 2's complement. Right, 2's complement form, to be precise. Now first we have to write it, say plus 73 plus 0.75 in 12 digit, we can write it as say 0100, then 1001.1100. In first method we will do the positive expression of the given number, then we will take one's complement, and then we will take the 2's complement. So we will write down this number here. Say we have 0 1 0 0 1 0 0 1.1100. So its one's complement will be 1 0 1 1 0 1 1 0 0.0011. So this one we can take as 2's complement by adding 1. So this 1 1 will be 0, borrow 1, 1 1 will be 0, again borrow 1, and 1 minus 1, so we'll get 0 minus 1, we'll get 1, here we'll get again borrow, that will be 0, and this side number will be as it is. So sign bit is minus here. So this is the answer. Now 2's complement arithmetic we can find out. 2's complement arithmetic means we can have addition and subtraction in 2's complement. So let us see some example. So we will have example, subtract 14 from 64 using the 8-bit 2's complement arithmetic, right? So say we'll write down the given number. We'll write down, we have to subtract 14 from 46. So first what we have to do, plus 14 we will write in the 1's complement, and then we will take 2's complement. Say plus 14 is equal to 0 0 0 0 1 1 1 0, and in 2's complement we will get it as 1 1 1 1 0 0 1 0. Okay, now let us check plus 46 minus 14. So here we can write it as say 0 0 1 0 1 1 1 0, then say plus 1 1 1 1 0 0 1 0. So then we can solve this. So here we'll get 0, here you get 0, 1 borrow, 1 1 0, then again 0, then here also 0, then 1, then 0, then 0, and 1 carry which we'll ignore. So MSB is 0, so the result is positive and it is normal binary form. Therefore the result is say plus 32. Now here is one example of binary addition. So let us see one more example. So say let us take next example. Say example is add minus 75 plus 26 using the 8-bit 2's complement arithmetic. So again same method, plus 75 will be say 0 1 0 0 1 0 1 1. We are taking 2's complement, 1 0 1 1 0 1 0 1. Okay. Then let us have these numbers, plus 26 minus 75. So here we will get say 0 0 0 1 1 0 1 0, then plus 1 0 1 1 0 1 0 1. So answer will be say, here will get 1, here will get 1 1 1, here will get 0, then here also will get 0, here will get 1, here will get 1. There is no carry. So MSB is 1, so result is negative and is in 2's complement form, and this value will come to 49. So normal subtraction also we get the same. Now let us see one more example here. Say example given as add minus 45.75 to plus 87.5 using 12-bit 2's complement arithmetic. So first let us see, this is with fraction. So say we have 87.5 and say we have minus 45.75. So our answer should be actually plus 41.75. So how we can convert it here? Say we have 0 1 0 1 and then we have 0 0 1 0 1 0 1 0 1 1 1.1 0 0 0 1 1 0 1 0 0 1 0 point 0 1 0 0. If we solve this, we'll get 1 1 0 0. Here we'll get 1 0 0. Here we'll get 1 0 1. Here we'll get 0 0. So we have to ignore the carry. We get one carry here that we ignore. So MSB is 0, so the result is positive and is normal binary form, and it will be same as 41.75. So these are some examples on addition. So with this example, I will stop this session here. In next session, we will see the next topic or next examples. Till then, thank you. Have a good day.